Okay, so coming to the crystallinity in polymers, now I told you that whenever we think about the properties of any material, crystallinity is one important thing that tells us a lot about that material and the manufacturability of that material. So how about polymers? Are they amorphous or crystalline? You would say they are amorphous, right? In most cases, now when you have these crazy chain-like structures, then there is no way that you can become crystalline, because crystallinity requires perfect order, arrangement, and we don't even work with atoms here and so on. Well, the point is, polymers have a different type of property that is known as semi-crystallinity. So many of them are amorphous. Many of them are amorphous, and you are correct. But some of them can also be what is known as semi-crystallinity or semi-crystalline material. So the name suggests that they are sort of half crystalline, half amorphous. What makes them crystalline? Why would they be crystalline at all? Well, in some cases, the polymer chains somehow organize themselves, because ultimately polymer chains do have some bonds on their surface. They also are able to form van der Waals bond with each other. They are able to, based on their chemical affinity, they are able to organize themselves also in certain regions. But in the case of polymers, because of the complicated shape, this cannot be the overall structure, but certain regions are often, they organize themselves, they order themselves. They're not atomic order, it's some sort of order of the chains or stacking of the sheets in the case of sheet-like structures. But those little regions then will become crystalline, and then there will always be some amorphous regions in the case of polymers. So when we are dealing with polymers, we need to know that we have both amorphous and crystalline regions in many cases, but in some cases it's completely amorphous. So maybe this image will help you. If the chains in a polymer are, they look like this, they are just completely random and maybe also entangled, in that case, this is an amorphous polymer. However, if some parts of these chains are able to organize themselves because of whatever intermolecular forces they have, in that case, those parts are crystalline, and then altogether you will have a semi-crystalline type of material. Okay. So what else? Something about the processing, something about the properties of the polymers. So we now know a few things about the chains, about the arrangement of chains and so on. What else? What other properties polymers can have? Why do we need polymers altogether, by the way? Why don't we still work with metals? Well, number one, metals we do not really synthesize. We do not have any control over their properties. But in the case of polymers, because we make them, we can actually induce different properties. We can actually induce different molecular weights and so on. Number two, polymers are carbon based. Carbon is a light element. Carbon and hydrogen, they are very light elements. And so altogether, the weight of the polymer compared to metals is much less. Right? So this is also one more advantage. And another advantage is that we are able to process them, although compared to metals, still we may not have so many techniques that are available for polymers, but we are able to process them in a reasonably convenient way, and often polymers are compatible with batch fabrication, batch manufacturing. So you can make a lot of them in one batch, which makes their industrial manufacturing relatively cheaper. These are some of the advantages. I may have written a few things here. Thermoplastics can be melted. Yeah, so about the processing of these polymers, well, how do we process them? If it can be melted and shaped, then this is what I'm going to do, right? So thermoplastics, for example, I melt them. If I want to make thin sheets, I put them inside a roller. If I want to make bottles, I just blow some air inside them and poof, it just comes out, the bottle comes out, and then you cool it down. So it's like these are different, and then you can also have molds, and you can perform different types of processes. You will learn more about it when we come more, towards manufacturing. Now it's just material introduction. So yeah, if we can melt something, then that is what we are going to use. Now these are my sunglasses. Why do I give the example of sunglasses? Because this was something which was made of glass. They are called glasses, right? So some 20 years back, there used to be still glasses in the shops, not even 20, maybe even 10 years back, I could find glasses that were made of glass, but now everything has switched to plastic. And this plastic, the one that is used in making the glass of the glasses, that is known as polycarbonate. Polycarbonate is a transparent polymer. So this is also one advantage of polymers. You can control the properties, right? So based on the chemical structure, you can also have transparent materials. So polymers such as polycarbonate, and there is also something called polymethyl methacrylate, PMMA. These are the materials that are transparent, and they have replaced glass for many applications. Now what you can have is, you can have really curved glasses. So people who are doing mountain biking, for example, or swimming glasses and all, you will see these are they have very high curvature, and that is not possible or extremely difficult when you use glass. Okay, also another advantage is you can drop them multiple times and they will not break. So there are properties in polymers that are of advantage compared to many other materials. So they may not always replace metals, but they can definitely replace glasses, they can replace other materials, and they can also make them more durable. All right. Okay, so yeah, also by the way, when we manufacture glasses, we often have this molding processes for making the glasses, okay, or the frame of the glasses, and many other plastic things. You can think of several examples. Okay, thermosetting polymers are often prepared by mixing two or more. So thermosetting is the one again that cross links. So there is some chemical thing going on there. Thermoplastics are often single component, so all chains were of the same type you saw in the previous slide. But in the case of thermosetting materials, you often have two or more components that are added together, and then because they are forming a chemical bond, there is some chemical reaction going on. That is the reason they cannot be converted back to their original components. So that is why what we do is, now if we have two or more components, let's say two components, then, and I know that once I mix those components, then they will solidify and then I cannot change anything. So what I will do is, I'll add both components inside a mold which has the shape that I wanted in my final product. I mix them in the right ratio, and then it solidifies after cross-linking anyway, and then I have the shape. So this is kind of the fundamental principle of thermosetting materials when we make something out of them. Okay, now some other properties. Polymers are typically thermally insulating. They are based on carbon. They do not have free electrons for movement, because often they have covalent bonds and so on. So they are in most cases electrically and thermally insulating, but there are some new polymers that people are working on. There are advanced polymers which are electrically conductive, not for us for the time being. Okay, one thing that kind of limits the application of polymers is the fact that they are not very high temperature withstanding materials. So most of them would actually degrade after 300 and even 200 in most cases. So in that case, most of their applications are limited to low temperature applications. Okay, so however, they are chemically very stable in general compared to many other things. So they do not go through corrosion, so they will not have rusting or these kind of problems, surface changes and so on. But they are stable, but over long periods of time they do leach out. So if you're using a water bottle and you keep on using it for 6 months, then that's not safe, because slowly the micro scale particles of the plastic will be removed from that. That is called leaching. And also similarly, if you have trash, if you have waste, polythene packaging materials somewhere on the ground, then slowly the microplastics will leach out and they will pollute the groundwater, they will pollute the crops and so on. So they are stable, but not so stable that you just can throw them anywhere or that you can use them forever and so on. So in principle, polymers are very important materials. Polymers are indeed essential in today's world, and we cannot think of a world where we don't have polymer. And I will tell you that you may think that now I can replace my polythene bag with paper bag or cloth bag, and you should do that. But for some applications you can replace plastics or polymers, but not for all the applications, because now we have become also to a great extent dependent on polymers for packaging materials. If you start packaging things in paper, how long will their shelf life will be so less, right? And you may end up ruining more food items then saving the planet by by removing the plastic. So it's a very complicated problem. The point is that polymers and plastics are very important, and on the next slide I'm going to show you some applications also. However, one important thing is that they should be recycled, and if possible, if it is not possible to recycle them, like in the case of thermosetting resins, then you convert them into other types of materials. So after their degradation, they can be also converted into fuels and different types of materials. So we need to basically get rid of the plastic after its use. So use it, but then segregate the waste properly and then recycle that waste. This is very important. Okay, so last slide, and this is something I don't have to tell you, but anyway, I had some pictures, so I thought I'd paste them. This is a water bottle from one of the teaching assistants of this course. And also, these are some things that are in my lab, in research lab. So there are all these things. They utilize plastics and polymers. This is an important thing. This is a COVID test kit. And these kind of testing kits, which are single-time use, these are disposable testing kits. A lot of similar devices, small single-use devices, are based on plastic. So this entire kit is more or less plastic. More than 90% plastic in this. So this is also an important use. A lot of medical equipment, in fact, also gloves, they are made of polymers. Like rubber is also a polymer. So a lot of medical equipment, a lot of things are made of polymers. Okay, this is a chair somewhere, and I'm sure you have also seen such chairs. A lot of furniture that is also made of plastic nowadays. Packaging material, of course, you know that a lot of packaging material is polythene and other types of polymers. There are also larger applications. For example, if you sit inside a car, you will see that there are multiple components that are made of in fact, the inside body, the interiors of the car nowadays, they're all made of plastics, and there are also different types of rubber like polymers and so on the seat of the car. So there are various parts that are made of polymers. Larger things also, like airplanes, also will have parts that are made of polymers. So certain things may not completely be made of polymers, but they'll definitely have some parts, right, here and there. The sports gear, there are several examples. So I think now this lecture ends here. You should also look for some examples of plastics and polymers. So again, polymer is the entire class, and plastic is a subset of that, right? And you should think of more examples, and you should also think about how you can do environment friendly manufacturing using plastics. And now the exact manufacturing processes we will learn a little bit later.